So hi everyone and welcome back to the channel. Now this one's been a long time coming as I've done a fair bit of testing with this and thinking of how to describe certain principles in this video without getting too nerdy. So there might be a little bit of maths, a little bit of physics, but it's all in the name of explaining how power meters work, so please do stick around. Now full disclosure again, Favero sent me these pedals, I did not buy them. They know now that a large portion of my career has been spent in torque, transducer design, power sensing in powertrain applications. I told them that. I said I would get pretty geeky on the strain gauges and diving into the technology, and they were still keen, they were still confident. Let's get straight to the point. I've said in previous videos on power meters that I normally avoid pedal-based power meters. But the Faveros have had such good reviews since their inception, maybe they can change my mind. Now, why would I normally avoid pedal-based power meters? I never thought it was a really good idea to put a sensitive strain gauge or torque transducer in a pedal body, because in my eyes, if you look at my old DUO-Shi pedals, which aren't actually that old, pedals I think are consumable items. The bindings get worn, the platform gets worn, and you can develop a bit of sort of vertical float between the cleat and the pedal. The bearings get worn inside. These DUO-Shi ones are actually serviceable because you can extract the ball bearings out of this outer bearing and adjust the preload and everything. Maybe these Faveros can change my mind because they've had such good reviews out there so far. Now, if you don't know how they work, basically this axle basically is the power meter, and this fits into a Shimano pedal body. Now, there aren't that many solutions out there for you because probably licensing and patenting issues with Shimano pedals. Now, you can pretty much put these in any SPDSL pedal from Shimano apart from the current DUO-Shi pedals. Because the DUO-Shi pedal has a completely different bearing layout. It's got some outboard bearings here, which are like cup and cone bearings, which you can adjust the preload on, take out any slop, and you can actually service those. So if you're running DUO-Shi pedals, you are going to have to pay a slight weight penalty and change down to Ultegras to be able to fit these power meter spindles. Like I've said before on the channel, really do not worry about weight renism. How many of you out there are sub 60 kilo Tour de France riders? Exactly.
Heavy is good, heavy is reliable. If it doesn't work, you can always hit him with it.
Now if we take a closer look at the technical elements of the spindle, it's actually quite interesting how they've designed it and packed all the electronics into quite a small system. Now we've got an anodized aluminium cartridge which houses the bearings, which are actually replaceable. So Favero will actually sell you, I think for 49 or 50 euros, a new cartridge with new bearings without affecting the factory calibration of the power meter. Basically all the sensor electronics are on the spindle and you keep the spindle. I've actually tested this spindle in the lab and they've not scrimped on materials here. This is a seriously well made piece of kit. I'm pretty sure this stainless steel is a 17.4 pH steel, which is exceptionally hard. To give you some picture of how strong that is, the yield strength of a 17.4 pH is probably around 1,000 megapascals. Now when I hardness tested this stainless steel, it came out as about Rockwell hardness 40, which is going to give you a tensile strength somewhere in the region of 1,000 megapascals. So this is a very strong high grade stainless steel. So it's really nice to see they've used that, not some cheapy stainless. And because there's such a large cantilever load on the pedal spindle, you actually do need some really strong materials. Let's address the elephant in the room. Now many reviewers have commented on these pedals that the extra Q factor or pedal stance offset or pedal stance width is basically a deal breaker that they can't live with. Now I'd like to consider that a bit more before kind of disregarding it so naively, because that seems like an easy thing on the spec sheet to just pick on. For me, the extra width that it gives the pedal, which in the case of an Ultegra is about 13 mil. So when you've got it set up next to the crank, the center of the pedal will end up 13 mil further away than a normal Shimano pedal. That's not an issue for me. Number one, biomechanically, I need a slightly wider stance anyway. So my cleats are maxed out on my shoes. The cleats are maxed out inboard, which moves the shoes further outboard to move my feet out. Biomechanically, that's just what I prefer for my bike fit. Number two, I actually have problems with heel rub on the chainstays due to having quite large feet and quite large shoes. So my shoes are 46.5 European size, which makes my heel very close to the chainstay. So I actually need to move the feet further out anyway to avoid heel rub when I'm sprinting. I've got a bit more width to the pedal. I can actually dial the cleats outboard a bit to bring the shoe back in. So I can actually account for that a little bit, so it's not such a big issue. And finally, number 3, my mountain bike XT cranks are a whopping 178 millimeters on the Q factor, whereas a Shimano Ultegra road crank is 146. So, and I never complain when I ride the mountain bike thinking the Q factor's too wide, I just deal with it, and most people don't even think about it. Like with the mountain bike compared to like a road crank, like I said, 178 mil Q factor versus 146 for Shimano cranks. Now that's about 16 mil on each side. Now with these, it's about 13 mil on each side, but I can dial back some of that with the cleats. So the total final offset, I imagine, will be about 7 or 8 mil wider than normal, so that's not really a problem in total. Let's talk a little bit about the principle of power measurement, and one thing that's always concerned me about pedal-based power meters, which is force offset, and where the force is applied down on the pedal. And how does the pedal know that force, and how does it know the distance? So before we go any further, quick lesson back at school, how we measure power at the crank on a bike. So we've got our chainring, we've got our crank pedal some distance away, let's call it L. We've got force at the pedal, call it F. And then the torque at the crank is just F times L. That gives us the torque. Now to work out the power, it's just torque times rotational speed. Pretty simple, right? With a spider-based power meter, we can just measure the torque directly at the spider, which is concentric with the crank. So we don't really need to worry about the crank length. With the pedal-based power meter, we need to measure this force F at the pedal, and then we need to times it by L. So you actually need to input your crank length when you're using a pedal-based power meter. So if we now look at this side, let's look at the pedal. How does it work? Well, we consider it as a pretty simple cantilever beam, fixed at the threads where it goes into the crank, and then a cantilever beam with a force applied somewhere near the middle of the beam, an arbitrary length down the beam. Now that force application point will change depending on your biomechanics, depending on your cleat setup, depending on your stance width. It can even change, per revolution. It might change when you start your ride. You might get tired, you might start pedaling funny, you might get sore feet, start pedaling on the outside. So this needs to decipher where you're applying the load. Anyway, we'll talk about that in a minute. So let's just draw that out in a really simple cantilever beam first. So we assume the beam is fixed at one end. Then we got our pedal axle and some force application point. And that force application point is a distance X from the fixed end. Now let's say we've got a pair of strain gauges. Now let's say the electronics designer wants 1,000 microstrain on that when the rider applies 1,000 newtons or around 100 kilos with his legs. Those are kind of arbitrary figures. We'll keep the figures easy for the math. The designer can tune the steel, can tune the thickness to get that microstrain. That's all fine. And they say, right, when the strain gauge reads, or when the Wheatstone bridge reads 1,000 microstrain, that gives out a certain millivolt output. It goes through an amplifier, goes through an ADC, which is an analog digital converter, and gives you a power number. All fine. Or gives you a torque number. All fine. But I can also get that 1,000 microstrain if I apply a force somewhere else down the beam. And if I apply a force further away from the strain gauge, I only have to apply a smaller force. So let's say I applied the force because of my dodgy leg biomechanics much further out on the pedal body. Let's say instead of applying the force in the middle, I started pressing with the outside of my foot here. Let's call that length 2x. Now if I'm applying the force twice as far away as I should be, I only need to apply half the force, 500 newtons. So does the power meter think I'm pressing with 50 kilos, or does it think I'm pressing with 100 kilos? And this has always been the problem of the early pedal-based power meters, is that they assumed you were always pushing your force down in the middle, which is completely untrue because of biomechanics and cleat position and stuff. You could be pressing here, close to the strain gauges, in which case, even if you push down with 100 kilos, the strain gauge would read very little and it would appear to be low power. Or you could push further away and it appear to be producing a lot more power. So how do the good pedal-based power meters get around this? And I think Favero is doing this because I've probed and probed and probed and tried to get some answers off them. And I also think the Garmin Vectors do this as well. If you set up another pair of gauges, then by comparing the bending moment on this one divided by this one, you can actually figure out where the load is applied. So if I apply the load here at the end, very far away from the two gauge pairs, and I know the distance, let's call the separation distance x prime. If I know this separation distance, then by comparing the ratio of this output over this one, I can actually figure out where the load is applied. So how does that work? So if I apply the load very far away, these two outputs are going to be very similar. Maybe 1000 microstrain and 800 microstrain, for instance. Let's just guess. If I apply a load much, much closer to the gauge pair, so x prime over x is a bigger relative proportion of this distance, then the ratios become different. So the current ratio, let's say if I apply the force at the end, the ratio of this one to this one is 8/10, which is 4/5. If I applied the load here, let's say we get, I don't know, it's closer in, so we're going to get less total strain. Let's say we get 500 on this one and 250 on this one. So then our ratio becomes 1/2. So by calibrating for this ratio and the absolute output of the Wheatstone bridge, we can not only decipher where the load is, but also how much load we're getting. Now, I think that some of the early pedal-based power meters weren't doing this, and they basically just had one strain gauge pair, and they assumed that you were going to apply your load somewhere in this window, this distance, and that distance over the distance from the gauges was acceptably small enough to basically ignore the error. That's really not good. That's a fudge. It's not the best way to do it. By doing this, so working out the absolute strain on the gauges and then looking at the bending moment ratio of this one to this one, then you can actually work out where the load is applied and what the load is. I hope that explains a bit how the best pedal-based power meters work. I'm pretty sure Favero are doing it in theirs. I probed and probed and probed about platform center offset and if they're going to offer that as a metric, and I'm pretty sure this is capable of doing it. It's another calibration factor. That was very, very long-winded and big nerd energy. Let me know if you've got any questions about that. Now, to install the units is very straightforward. So you get a left pedal, you get a left spindle, and you undo this lock nut and you do this one up. I would be very accurate with your torques. So strain gauges are very sensitive to what are called boundary constraints or boundary conditions, end effects. So threaded parts, how tight you do that up onto the crank. There needs to be a washer on here if you haven't got adequate spacing between the electronics pod and the crank. That's very important. If you don't, when you screw that into the crank, you'll crush this. So it says in the manual you might need to apply some pedal washers, which they give you. I think they give you up to 2 mil to space that off the crank, because some crank have their threaded inserts quite inset, like especially the carbon crank ones. So be aware of that and do them up to the torque that's specified in the manual, because that needs to be on tight. So normally when I do pedals, I kind of just nip them up, but these really need to be done to the right torque because it could affect the strain gauge readings, and that's the same with this kind of locking ring on the cartridge. Unthread that Ultegra pedal body in with the left Favero one. Now the left pedal, if you're looking at it like this, the thread does up in the regular direction. The right hand pedal would be opposite to what you expect. So let's get into the testing. Now before we get into the data, you may recognise these two Wallies on the screen. That's Francis K. He's got a massive YouTube channel, great following, and he works a lot with Bike Fit James from Bicycle Richmond in the UK. Now James is one of the most highly regarded bike fitters in the UK and Europe, so I thought if there's anyone to ask about the increased stance width or Q factor that these pedals are going to give you, it's going to be him. And I said, you know, how many customers come in for a bike fit and you prescribe them a narrower Q factor or a wider Q factor? How does this going to stand in the market? And he said, well, actually, road cyclists, racers and non-racers are pretty fickle. 60%, he reckoned, of his customers could use some sort of stance increase. And that was pretty surprising. So don't be fickle. Don't knock these before you've tried something with a slightly wider stance increase. As I said, a lot of people own a mountain bike as well, so you're jumping to a much wider Q factor anyway, and no one complains about that. Secondly, I'm not going to use the DC Rainmaker tool for power meter comparison you may have seen on GP Llama's channel. That's a great tool. It helps save time, it syncs up the timestamps, and you can plot many different power meters and head units on the same graph for really, really quick kind of graphical evaluation. I'm actually going to use a mixture of Python and Excel to help spot the trends that I might miss if I just plugged it into that. But basically, I'm just cheap. I'm not going to use that because it's $29 a year. But yeah, it's great software. Also, I'm not going to use an indoor trainer. I want to see vibrations that could affect accelerometers in the Quark and the gyros in the Favero, and I want to pick these up on the road. Now, this might not happen on the indoor trainer when everything is stationary and smooth. Also, angular velocity variations during each crank revolution outside are more common than they are on the indoor trainer. So that's when you're doing slow climbs and also descending. Crank velocity isn't actually smooth, it's actually sinusoidal. I tend to think you pedal with a higher, smoother cadence on the indoor trainer because of the flywheel speed and things like that. Also, parasitic bending of the cranks on an indoor trainer is not really representative of what you're getting outside, and obviously parasitic bending can lead to erroneous power readings through the strain gauges, so I want to pick that up as well. And the Wahoo Kicker power calculation is based on flywheel inertia, spin down drag, cadence approximation, and current sensing, which is coming from the torque from the braking and the electromagnetic flywheel. There's also a fudge factor applied to the drivetrain losses in theory to match the crank power, and that's not really a direct comparison. The data, I've got loads of data for many different rides. I've got shorter 1 to 4 minute kind of hill reps, I've got sprints and some much longer steady state efforts to compare, and then at the end we'll also talk about cadence sensing and Favero's kind of pride and joy, the IAV, instantaneous angular velocity reporting. So let's look at the first bit of data. This is a seated climb. This just happened to be one of the first ever efforts I did with the Favero versus the Quark, and we can see the average power's spot on. There's not really much we can decipher from this graph. This isn't smooth, this is raw data. This is reported at 1 Hertz from the Garmin. We can see there's that power spike near kind of 550 watts, and the Favero lags by about a second on the peak power, and we'll get to that in a minute. But overall average power for that interval, I think that interval was about 3.5, 4 minutes, no difference. Seated climb number 2, very similar story. Difference was tiny, 0.2%, can't really notice anything. Again, the peak power on the Favero is reported slightly later than the Quark, but that could be a Garmin thing because they only actually read at 1 Hertz, or they only report at 1 Hertz through the Garmin. So we don't actually see the raw data from the power meter, we see the data after it's come from the Garmin. But yeah, average power for those 2 efforts is really not much you can say. They're very, very consistent. So it was a bit of a few moment for me, knowing that the Faveros are going to be as good as a training tool as my Quark's been for the last 4 years, at least now anyway, after a couple of months of riding. Now we went to a standing climb. We see a bit more difference in power, about 1.1%. I think this was about a 2-minute climb out of the saddle. But yeah, 1% can live with that. No real outliers on that chart. Now into some uphill sprints. This is a 30-second plot. It's delayed by about a second. The total work done, so the area under the graph, basically the same. I don't know what that reporting difference is. These timestamps are perfectly synced, by the way, in the raw data. So it's not as if I've got 1 second later versus it is timestamped sync. So not really sure what's going on there. But again, the peak power between the two, I mean, 5 watts in 1200 watts is nothing. So it's really impressed with that. I mean, I'm not saying my Quark is correct, but I'm just relieved it's basically the same. Another sprint. Slightly higher power this time. Again, it's a 30-second plot. We see that slight delay in the Favero. I'm not sure if that's a Garmin thing or a Favero thing. A slightly larger difference in peak power, but only about 20 watts. So at that power, that's pretty low. Pretty impressed it's picking up the little transient before the peak power event. So we got this little bump in both power meters before the peak power event. That's quite nice to see. And then sprint 3. So this is a longer sprint. I think the total out of the saddle time was about 30 seconds, and averaging about 900 watts. Max power is higher on the Favero towards the end. Don't really know why. So we got 1084 max for the Quark and 1136 for the Favero, but overall, you see the transients are mapped very well together. It's just that 1 second delay in the Favero, even though the timestamps are synced. Now, let's look at the lap summary from that ride. So that ride was more of a kind of hill rep training interval ride, did some hill reps and some sprints, so not steady state in any way of the word. Total normalized power for the ride, 301 on the Favero, Quark 305, so about 1.5% in on normalized power. And I normally go by how I feel, how hard a ride feels. When I look back at it in training log, I would look at normalized power, not really average. And we can see across the board, like some of those laps we just looked at, the power is very, very similar. So first climbing interval, 313, 313. Then we've got a downhill, then lap 3, 367, 366, almost spot on, and then a downhill again. And to be honest, all the intervals, the power of the actual power intervals were very consistent. Where we do see a difference is in the cadence. So on the left axis, you've got power. On the bottom, you've got lap number, or interval number, and up the right, you've got cadence. Now, I've plotted the cadence lines at the top, and you can see a massive difference in cadence for the lap 2, which was actually a downhill. So you've got 56 RPM average versus 66 RPM for the Favero. This is interesting. I've never noticed this about my Quark before, but I think because the Quark's resolution or kind of sampling rate of crank velocity is so much lower because it doesn't have a gyro in it, using an accelerometer. I think for those kind of moments when you're descending and you're putting in like half pedal revs or quarter pedal revs to change your outside foot and get comfortable on the bike, it just doesn't report any cadence. It just reports a 0 cadence, which drags the whole average cadence down. But you can, if you look at the power, 66 and 66 for lap 2, it's very, very similar. So whatever average torque it's reporting for that cycle must be higher to make up that difference, because obviously power is the product of cadence and torque. So I'm not too worried about that from the Quark. Like, it just goes to show how good the Favero is at reporting cadence, because it can actually report those small, not even full rotations of the pedal stroke to log a power and a cadence for that sample. Now, just to get a better picture of that, I plotted cadence error against power error, and you can obviously see at the higher cadence differences between the two power meters, there's a much higher power error. But those are all like the downhills. Where there's hardly any error is the kind of actual pedaling intervals. So I'm not too worried about the downhills, but it's just interesting to see the difference. I plotted a line of best fit. The correlation is not great at best, but yeah, just quite interesting to see that. Now, this is another ride, completely different day. This is what we think is a steady state interval. So this was a flat route. Basically, there's no junctions, no traffic lights. There's a roundabout at each end, very similar to a TT course. And it's more or less flat. It's undulating, but it's more or less flat. Now, when you think a ride outdoors is steady state and you look at this raw power on all these dots all over the place, you realize it really isn't steady state. This is nothing like erg mode on the trainer. And even, the kind of most constant ride outside, when you actually look at the raw power data, it's all over the place. So what I've done is I've plotted a 40-second moving average for both. The pink line is the Favero, the yellow line is for the Quark. The average power for the whole lap, the 50-minute interval, was 230 and 234, so 1.5% difference, pretty spot on. And what you can see here is obviously the power does fluctuate, even if you think you're doing a steady state interval. You've got little micro rests, you've got a little bit of descending, a little bit of climbing, so you get these power peaks and troughs here and there. But what's interesting to see is there's no deviation, so the line is almost on top of each other for both power meters, and they don't deviate from 0 minute to 50 minutes. It's pretty constant all the way through, and that's really what you want over a long interval, maybe where you might pick up some hysteresis in the sensor, some viscoelastic creep of the strain gauges, or even temperature changes through the ride. You want to see there's no divergence between the two power meters, and here there really isn't. They're pretty much spot on. Then I had a little 10-minute easy pedal, and then back into a kind of low effort 50-minute interval on exactly the same course, on exactly the same day. And we've got a difference of 1.3% between the two power meters. Again, no divergence between the start and the end. So from 0 minute to 50 minutes, the power meters are pretty much bang on top of each other. And the lap summary of that ride, lap 1 was a warm-up, 202, 204, so within 1%. Lap 2 and 3 were the 50-minute plots we just looked at, 230, 234, 199, 203, so almost bang on. And lap 4 was, a coasting down, very gentle. You can see again that massive difference in cadence reporting of the Cork versus the Favero. I just think when you're coasting or half pedaling, the Cork just doesn't log any cadence, which drags that cadence reporting down. Cadence error versus power error. Now we see the power errors are much, much lower on these steady state efforts. Where they deviate is on those, peaky efforts, where I think the Cork doesn't do such a good job. Now I just want to talk a little bit about cadence sensing and why I really do value this gyro that's in the Favero. So there's a number of different ways you can measure cadence on the bike, and we'll discuss briefly the pros and cons between both. You've got magnets, okay, so static magnets on the frame with a pickup inside the crank or something. Now we've seen that on Pioneer, we've seen that on like Shimano power meters. Pros of that: cost, it's cheap, the sensor's cheap, the magnet's cheap, and it's pretty simple. Cons of that: low resolution. You basically get one reading per crank revolution, so you can't really do much integration through the power. You can't really do much integration through the revolution, and you've got these static parts on the frame which can get knocked off. Accelerometers like we've got in the Cork and many other power meters. So it's on board the chip, it's all sealed inside, so you haven't got that durability issue. Low power consumption, again though, pretty low resolution, and they're very easily saturated by external vibrations. Now, the way accelerometer works is basically to pick up vibrations. It's not really designed to pick up angular velocity. It does that kind of indirectly. So it is there, it is there as a vibration sensor. So there's a lot of filtering required to filter out the things you don't want from the road vibration, which is again one of the reasons why I wanted to test the Cork outside. We've got gyros like we've got in Favero, much higher resolution, and the good thing about a gyro is it's designed to output angular velocity. So it outputs millivolts per degrees per second, which is a direct, velocity measurement or cadence measurement. It, in design, has pretty good rejection of high vibrations, so the vibration of the road shouldn't be so much of a problem. Slightly more expensive than an accelerometer, but not too much. So that's really the only con. And finally, you've got like magnetic encoders, which would be really the best way to do it, but packaging would be an issue. They have to be external, probably have to sit on the crank, so durability is an issue, cost is an issue. But if you've got any like really high spec indoor erg for bike fitting or something, I'd put an encoder on that. But until frame designers start like designing in packaging areas on the bike for encoders, it's just not going to work, and it's quite hard to onboard on a chip. You really want it kind of external as a separate part, which means protecting it and things like that is quite impractical. But the good thing about like I said before, the Favero is this instantaneous angular velocity. Now most bike power meters will only measure crank velocity once per revolution, and they will average the torque for that revolution times the two together, and you'll get power for one revolution. But what actually happens when you pedal is the speed is not constant. You have this kind of peanut-shaped speed profile, and the torque shape is not constant either. And you really need to kind of sum all these samples of torque and speed, multiply them together, and then divide by the number of samples you've got to get your kind of revolution power. And that's exactly what the Favero does. It's a much more accurate way of doing it, and it's definitely not what you get on the turbo train. Like the turbo trainers are so far away from this kind of accuracy. Anyway, huge power meter test. Really hope you enjoyed that. Let me know if you've got any questions down below, and any more tests you want me to do on power meters, let me know. Don't forget to like and subscribe. Cheers, and I'll see you in the next one.